Welcome back to linear algebra. We're going to start off with Anki. What is the effect on the solution set of a linear system if an elementary row operation is performed on its corresponding augmented matrix? No change. What is a system of linear equations, also called a linear system? Well, it's a finite set of linear equations. Wow, nice. Hold on, that one is old. I want to just see how long. Next time we'll see that is in 3.5 months. What three basic algebraic operations can you perform on the equations of a linear system without altering its solution set? What three basic algebraic operations can you perform on the equations of a linear system without altering its solution set? Okay. You can multiply. Is it asking three basic algebraic operations, right? Perform equations of a linear system. Okay. You can multiply one equation through by a non-zero constant. You can add one row to another, or you can add a multiple of one row to another. Interchange two equations, so we'll see that again tomorrow. All right. So we were dealing with this problem yesterday that I just couldn't figure out how to do. It was like showing that if this equation is true, then A is interchangeable, or not interchangeable, A is invertible, and then finding the inverse. So I don't really know what that means. I know what it means, but I couldn't figure it out. So I'm just going to jump into Quizlet and figure out where I went wrong. All right, guys, this is exactly why I cut the bleeding yesterday. I didn't just keep working on this for the next few days because it was way simpler than all these entries and stuff. It was literally, you just manipulate the problem like algebra, essentially. Subtract both sides by I. Multiply both sides by negative 1. So that you just get this equals I, and then you pull out the A, distribute the negative, you factor out the A, distribute the negatives, then it's A times, in parentheses, negative A minus 2, which is times the identity. That's an implied identity whenever you're dealing with polynomials. This is a polynomial, right? This is a polynomial, matrix polynomial, so we imply the I equals I, so then we know that, this is the definition essentially of an inverse. So we know that this, and the inverse is this, is just flipped back, reflected, negative A minus 2I. All right. So we missed that problem. Where art thou? 33A, okay. So now we're going to continue working through more problems. I'll be back in a bit to recall what I learned. Alright guys, I'm not going to lie, this stuff's getting pretty difficult, but yep. I wish I had some more proof experience because a lot of this stuff is show and prove, but anyway, we're just going to keep doing our best, and keep pushing through and see where it can take us someday. It was basically to find the inverse of this, or find x, find the inverse of A. I couldn't understand what to say. So solve this equation, that was the hint, by equating the corresponding entries on the two sides. I tried to do this, but I realized it's not just going to be zeros and ones. It's going to be more complicated than zeros and ones. Maybe I could figure it out like that. Oh my gosh. Oh my gosh, could I do that? Could I use like symbols and then, hold up, check this out. I don't know if this is how you're supposed to solve it, or the way the book at least is intending to solve it, but what if I went like that, then used variables, and here these are unknowns, A, B, C, D, E, F, G, H, I, and then equals in the identity matrix. What if I went like that? And then what I did was I multiplied it out, so A plus 0 plus G equals row 1, column 1, 1. I don't know. This is going to be a system of linear equations, is it not? With 9 unknowns? All right. My time's up for today, but I really want to try this out, so I'll be back in a sec. Can you believe that? Let's go. Yeah, I just basically put in variables and then ran the equations and then solved. Basically like substitution, elimination. Wow. Let's go. All right. Um, 41 was showing that basically if R is a row vector and C is a column vector, that R times C equals trace times C, trace of C times R. And I basically just, this is how I did it. I don't know if this is a great way to show it, but I did show it. It's not maybe that well written, but I did R and C, that's going to be this. And then I did the trace. So first of all, it's going to be an n by n when you times C by R. And then I kind of drew it out, and then I drew the outline with the traces, which sums back to this, and these things are equal. The only difference being, what do you call it? Commutative law of multiplication. So I think I can just say RC equals TR, CR. All right, and then I can say R1C1 plus R2C2 plus dot 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 plus RNCN equals C1R1 plus C2R2 plus dot 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 plus CNRN. All right, we went from, these are 2 hard problems to, well, we might have got 2 of these right. So that's it for today. Talk to you tomorrow. See ya.